Okay, so just welcome you to this second session of this afternoon, which will be on thermal and mechanical properties. So we have two different modules that are inside AFLOW to calculate these properties. We have the AFLOW-AEL module, which calculates elastic properties, and the AFLOW-AGL module, which is basically a Debye model, which calculates thermal properties. I'm just going to turn off my camera now, so to save some bandwidth. So why are we interested in these types of properties? Well, here's some example applications. So I already mentioned some of these on the first slide. In the very first session on Tuesday morning. But for example, for mechanical properties, you might want to find super hard wear-resistant coatings to put on things like drill bits, for example, for oil drilling or for machine tools. You might be looking for thermal barrier coatings, for example, for aerospace or energy production applications. So for inside gas turbines, the turbine blades tend to be exposed to very high temperatures and a very corrosive environment from the exhaust gases. So you want something that's going to protect the turbine blades from failure due to things like creep and deformation. So here you put a coating on top. So you want something that has a low thermal conductivity, so it's going to actually protect the interior of the blade, but at the same time you want something that has a thermal expansion that matches reasonably well with the turbine blade material, because you want something that you're not going to get any cracking or essentially splitting off the material from the substrate. You also probably want something that's still reasonably mechanically strong. So you might want to also have a reasonably as high an elastic modulus as possible. So you're trying to balance these things, these different properties, and you're trying to find the optimum material for this kind of an application. Another application that I mentioned was heat sinks for example, for computer chips. So here you want something that has a high thermal conductivity and high heat capacity, so it's going to take heat away from the chip. Then there would be another example in sort of electronics would be thermoelectric materials. In this case, to maximize the thermoelectric efficiency, you want to have a very low thermal conductivity. Okay, so how do we calculate these things? Well, it's the same principle that we've showed you for a lot of the other, especially like in the previous thing in POC, where we basically do a set of different DFT calculations. So we basically build an ensemble of DFT calculations. For the elastic properties, what we do is we take your normal relaxed structure and then we apply a set of normal and shear strains to it. So normal strains are basically like linear strains, whereas shear strains are going to be more like where you sort of more of a distortion that looks something like this. And the protocol we follow is we apply four normal strains and four shear strains in each independent direction. So 2 expansion and 2 compression. So depending on the symmetry of the material, you'll have a different number of independent directions. So in cubic materials, you only have to apply 8 strains, but in say an orthorhombic material, you would have to apply 24 in total. And so usually the default for the maximum applied strain is 1%, but this again is something that we can set, and it's something we actually change sometimes depending on the material. So for softer materials, you sometimes have to apply larger strains to get a reasonably high stress, so that you don't get too much numerical noise. Okay, so then for these different strain structures, we do a DFT calculation and we get the stress tensor. So this is these are essentially a set of pressures on each of the face in each different direction. So we apply one strain. Here's an example. So this is a strain in the 100 direction of the cell. Then you'll have a stress tensor. So you'll have the stresses along each direction. So these are the normal stresses, and these are the shear stresses. And then from these shear stresses, you basically get a set of equations. So sigma 11 equals C11, epsilon 11, and so on. And from these, you can calculate C11, C12, C13, and so on. And then for the next strain, you get this column and so on. And this is the what's called the elastic stiffness tensor, or the elastic constants. And this is what's called Voigt notation. So in practice, the full elastic tensor is actually a 3 by 3 by 3 by 3 tensor. But here you can actually reduce it because of symmetry. So a lot of these elastic constants are basically the same because of symmetry. And you can reduce it to 6 by 6 tensor. And depending on the symmetry of the material, you only have a few of these are actually independent. So for example, for cubic materials, C11, C22, and C33 are all the same value. C12, C13, and C23 are all the same value. And C44, C55, and C66 will all have the same value. And all the other entries are 0. The other thing is that this elastic tensor should always be symmetric about this diagonal. And that's actually a good test that we do in our calculations. So we check that, make sure that this tensor is symmetric. And if it's not, we might have to do something like increasing, for example, changing some of the calculation parameters. And then another thing we can calculate is what's called a compliance tensor, Sij, which is the inverse of this stiffness tensor. Okay, so from these elastic constants, we can then calculate the bulk modulus. So this is what's called the Voigt approximation, and this is the Royce approximation. And we have the same thing for the shear modulus, the Voigt and the Royce. So the Voigt approximation is based on the assumption that you have uniform strain. So these are for polycrystalline materials, so you have different grains. And for the Voigt approximation, you assume that the strain is uniform across all the grains, and the stress is supported by the individual grains in parallel. And this tends to give an upper bound on the elastic moduli. In contrast, in the Royce approximation, you assume that the stress is uniform across all the grains, and that the strain is then the sum of the strains of the individual grains in series. And this gives a lower bound on these elastic moduli. So then you can take an average, so this average of this upper bound and an average of the lower bound, and you get what's called this VRH average. So this is the Voigt-Royce-Hill average. So it's just a simple simple arithmetic average of these two upper and lower bounds. And this is usually the value that we consider the value that we generally use if we want to quote a value for these. And if you want to search our database for a value, this is generally the value we would recommend as probably being the most representative of the actual experimental measurements. And then finally, you can combine the bulk modulus and the shear modulus to get other properties such as the Poisson ratio, which is a measure of how basically the width of a material will change as you elongate. So if you have a sample of a material and you start stretching it along one axis, it will tell you how much the size will change in the other two axes. So that's how we do the elastic properties. Then we also have implemented the Debye-Gruneisen model to calculate thermal properties. So this is probably the simplest method you can use to calculate thermal properties. Let me see if there's any chance. So in this case, we do isotropic expansions and compressions of the cell, of the unit cell. We then calculate the energy for each of these different size cells. So we calculate the energy as a function of volume with Dft. Once we have this energy volume, we then fit this by a polynomial. Or you can fit to an equation of state as well. So there's things like Birch-Mernahan equation of state. So these are different options within AGL. So within AFLOW, you can select within the input file which ones you want to select, which if you want to do a different equation of state. Then from this, you can get the bulk modulus. So this is sort of a static bulk modulus based on the energy volume. From the bulk modulus as a function of volume, you can then get the Debye temperature as a function of volume. And so one term in particular to note here is this, there's this function, this is a function of the Poisson ratio mu. So it's quite a complicated function. You can check inside one of these papers and you can see the exact form of this function. So the other terms, this is the bulk modulus, this is the mass, this is some cell mass, cell volume, pi, this is h bar, so Planck's constant, and this is Boltzmann's constant. So once we have the Debye temperature as a function of volume, then we can start calculating things like the vibrational free energy as a function of volume, where this is the Debye temperature, and this is another function. So it's an integral over basically the cube of the Debye temperature. So you can again look inside these papers for more details on the exact form of all these equations. Once you have this, and then this is the number of atoms in the cell. So once you have the vibration energy, then you can add this as a function of volume. You can add this to the DFT energy as a function of volume and the pressure volume term. So now we have the temperature dependence and the volume dependence, and this gives us the Gibbs free energy. And once again, you can fit this Gibbs free energy by a polynomial. You find the minimum, and this will give you the equilibrium volume as a function of pressure and temperature. So you can do this for a different range of pressures and temperatures once you have your energy volume curve. And for this, you can get your Gibbs free energy and your equilibrium volume as a function of pressure and temperature. So now we have our Debye temperature at the equilibrium volume. We can calculate things like the Grunheisen parameter, which is a measure of how the Debye temperature varies as a function of volume. And it's basically a measure of the anharmonicity of the crystal. So if you have a perfectly harmonic crystal, this energy volume curve will be a perfect parabola, which means that its second derivative, if you think of it, so this was what the bulk modulus was, will be a constant because it's a quadratic. But if it deviates in real materials, this is going to deviate from a perfect parabola. So you're going to have some anharmonicity. And this is what gives rise to things like phonon-phonon scattering. It gives rise to thermal expansion, all these types of properties. And so this is quite important for calculating the Grunheisen parameter. It's something that's quite important to estimate these properties. We also have a term what's called the acoustic Debye temperature, which is essentially the normal Debye temperature divided by the cubed root. Well, an approximation to it is the normal Debye temperature divided by the cubed root of the number of atoms in the cell, in the primitive cell. So this is really an estimate of the Debye temperature that's only taking into account what are called the acoustic phonon modes into consideration. And Marco is going to go into more detail about what we mean by acoustic modes and optical modes in the next session. But for now, we just have to think that this, basically the Debye temperature and the Grunheisen parameter can be combined into this complex equation to estimate the thermal conductivity. And this is really only, this specific equation is really only valid more for cubic materials. It can be used to estimate other materials, but the reliability tends to go down as the symmetry of the material goes down. And then you can also estimate it at other temperatures. So you can use this 1/T approximation for the dependence of the thermal property of the thermal conductivity on temperature. So this equation gives you the thermal conductivity at this acoustic Debye temperature. Then you can estimate at other temperatures basically by incorporating this 1/T dependence. So you basically divide the acoustic Debye temperature by the temperature you want and multiply this by this thermal conductivity term, and this will give you a thermal conductivity at some other temperature. Okay, so just to give you an idea of how this works for different types of materials. On the left-hand side, we have our Debye temperature. So here's the, on this axis is our calculations. On the y-axis, on the x-axis, we have experimental values. And you can see for the Debye temperature, we actually get reasonably accurate results with some underestimates for some wort-site structures. So this is the top two, this is the zinc blende or diamond type structure. This is the rock salt structure. So these are both cubic structures. And then wort-site is a hexagonal structure. On the right, we have this lattice thermal conductivity. So we estimate this at 300K and compare it to experiment. You see that in general, we actually get a reasonably good trend for this. However, you can see that we have a general tendency to underestimate. So here's the experimental values. So the experimental values tends to be higher than the corresponding calculated value. This is because the method tends to overestimate the Grunheisen parameter. This is what we found. The method tends to overestimate the Grunheisen parameter, and because the Grunheisen parameter is in the denominator for this equation, it tends to result in an underestimation of the thermal conductivity. So the correlation here with experimental results, so this is how close this is to a straight line, is about 0.9. So this is pretty good. Generally speaking, even if it doesn't get the exact right value, it's still pretty useful for determining trends and identifying materials that are potentially very high or very low thermal conductivity, for example. So it's quite suitable for rapid screening, because Marco will show you in the next session how to calculate these things more accurately, but it's more computationally expensive, especially for more complex materials. And then using this, if we use this AEL Poisson ratio, instead of just estimating, so we can use an estimate of 0.25. This is sort of like a default Poisson ratio, but if we actually calculate it with AEL and incorporate it into the workflow, so we do a combined workflow, we can improve the correlation by about 5%. Okay, so this combined workflow has been run for about 6,000 materials in the database. This data is now available online at aflow.org. It's also accessible by the AFLOW REST API and the AFLOW Search API, so as I showed you yesterday. And then, so some of the more useful keywords, again, we kind of touched on this a bit yesterday. So for the bulk modulus, you use AEL _ bulk _ modulus _ VRH. For the shear modulus, we use AEL _ shear modulus _ VRH. So these both give you the voice, Royce, Hill approximations. You can also get the voice and the Royce values just by changing this to Voigt or Royce. And you can get things like the Poisson ratio as well. So some thermal properties keywords are the AGL _ Debye, AGL _ Gruneisen, heat capacity at 300 Kelvin. So this is CV, so this is constant volume. So this is the thermal conductivity at 300 Kelvin and thermal expansion at 300 Kelvin. Okay, so now to go into the technical details of how we actually would run these calculations. So if you look inside your AFLOW.in file that you've generated with the AFLOW _ proto command, you'll see this line that's commented out. So there'll be a hashtag sign in front of it. Okay, so someone asked if we can get the C11, C12, and C13 parameters. So you can get the full elastic constants, and I'll show you which file they're in once we start doing the exercises. But I can actually show you, if I pick an example, I can show this online. Okay. So if I open up the search, I do a search, let's say silicon carbide. I want to do mechanical properties and do bulk modulus VRH. So you can't access the individual values. Here, I just want to find one that has the value calculated. So if I go to the API, let's see if this is uncommented or not. So here, what you can do is you can download one of these files. So for example, here's the elastic constant, here's the elastic tensor in JSON format. So you can see you can get C11, C12, etc. from an actual file. But you can't do a search on these values because it's kind of complicated to do searches on individual values. But you can download the tensor if you have a material that this has been calculated for and that you're interested in. Okay, so now we'll just go back to the slides. So this line is, so you would uncomment this line to run an AEL calculation. Here's some other useful ones. So you can control like the number of normal strains applied, number of shear strains applied, the size of the strain step, and the normal and shear strain steps. You can also control whether you use symmetry to reduce the number of independent directions. So if this strain symmetry is on, for example, it'll only apply one set of normal and shear strains, for example, for a cubic material, but you might want to do a test to see how well it's working. So you can switch this to off and make sure you get the same values of C11, C12, C22, and C33, for example. And this will apply the strains in all the directions. To actually run the calculations for a set of strain structures, you will use this command aflow --multi --d and the direction path. So this will basically descend into each one of the subdirectories that you create and run all of those calculations. But we're not going to do this today just because it's actually quite a lot of calculations and will take a very long time. But if you want to try and use AFLOW yourselves on your own machines, then you can do this. Okay, and then we're going to look at the first set of exercises on AEL. We're not going to go to the rooms just yet. I'll just show you a little bit about where the file is, how it looks first. So first exercise is to make a copy of this. If you go to this 08 Thermomechanical /AEL directory, you'll see a directory called NGO, so it's for magnesium oxide, an example. So you can comment the appropriate line to run an AEL calculation, and then you rename the lock file to something else so you can actually do a run. So in the next exercise will be to run the command aflow ---- run equals 1 to create the subdirectories for this calculation. Then you make another copy of this directory. Again, you should rename the lock file and uncomment the AEL line, the line to run an AEL calculation. And then you switch off, then you change the command to generate determine the number of to use symmetry to determine the number of independents to off, and then check how many subdirectories are created. And then the last one, you go into a separate directory where the calculations have already been run. You uncomment the appropriate line to run an AEL calculation. You should also rename the lock file here and then run this command aflow ---- run equals 1. And then you can look inside this aflow.ael.out file, and then you can find things like the values of the bulk and shear moduli, and you can also see things like the elastic constants. So I'll just show you a quick example of how to do this. So where you need to go and see where the files are. So if we go to 08 Thermomechanical, do ls, so we see AEL and AGL. So we do AEL first. So we go inside. So here is a README. This just gives you the exercises. This file is the actual, basically the instruction manual for the AEL, for the AEL module. So you can read through it. You can see what the different options do. You can see what different types of results you can get, etc. But first I'm going to look inside this NGO directory and just show you the input file. Okay. So here's the normal input file, and here's the relevant part. So you can see here this. So when you generate one of these files, this will be commented out. So if you uncomment this, so you basically delete this hashtag, and then the AFLOW will know that it's an AEL calculation that you want to run. So here's the line to do the strain symmetry. Here's the number of normal and shear strains. Then this will check that the symmetry, that the elastic tensor you get is symmetric, and it'll print a warning message if the symmetry of the tensor is not, if the values are not close enough to being, if the diagonally, if the two op values on the opposite sides of the diagonal are outside of a certain tolerance, then it will write an error message. Then you can also write additional output values if you set this to on. So here's negative strains. So you basically, this will determine whether you do both compressive and expansive strains or just expansive strains. There are some properties to do with VASP. And then there's some properties here. So if you're having some problems with, like say, one of the calculations doesn't converge, because there's a certain amount of redundancy, you can actually skip up to a certain number of runs in each direction. So here we have the maximum value you can skip is 1. Okay, so I'll just, so you would, just to show you how to do this, you copy a directory, let's call it 1. Sorry. NGO1. Then I'm going to rename the lock file first of all to something like lock.old. And then open up the AFLOW.in file. And we can go down, and then we will uncomment this to actually run the calculation. Voila. And then you would type aflow ---- run equals 1. Okay, so now I think we can probably split up into our breakout rooms. And you can go and you work through these exercises in the individual small groups. Okay, so somebody has a question about how, if you can get these elastic properties at various temperatures. To a certain extent, yes. You can at least so for the bulk modulus, I'm actually going to show you how to do that. That's actually, you can do that with AGL, and I'm going to show you how to do that now. Well, first, let me just run through the different examples. So let me share my screen.
To share your screen?
Yeah. Okay. So let me just run through these very quickly. We have inside the first one, this one was run with the, so if we look inside this file, we have the strain symmetry on, and we get 8 files. So 4 normal strains and 4 shear strains. And let me just delete the lock file. I'll just show you when it runs what's going on. So here's doing the usual. Now it's creating the different strains, and now it's writing directories. So here's O2. So this is with the symmetry off, and now you get 24 files. So you get 4 normal strains in each direction in X, Y, Z, and 4 shear strains in X, Y, Z. Now we have the output files. So here's the main output file, and I'm going to open this up just to show you inside. Okay, so here's, again, it's keyword value pairs. So these are the same keywords that are used by the API. And you can see also we have the units. So we have bulk modulus, shear modulus, Young's modulus. We also have speed of sound, and then we have the elastic constants down here. So here's the C11, C22, C33, C12, C13, C23, and then C44, C55, and C56. Okay. Okay, so somebody has a question about how this compares to ATAT. Okay, I'm not sure how ATAT does elastic constants. I'd have to look it up. It's probably a fairly similar method though. Pretty much, so, okay, let me step back. There's 2 main methods of doing elastic constant calculations. There's this method, which is the stress strain method. And then there's the method that's based on energies. So you basically do volume conserving strains. And then you have for each, depending on the symmetry direction, you have a set of volume conserving strains, and then you calculate the energy, and then you fit the energy to get the elastic constants. This is a bit more involved, where the advantage of the second method is that not every DFT code will calculate the stress tensor. Thing is, if you have access to the stress tensor, you have access to a lot more information than just the energy. So you can actually reduce the number of calculations that you actually have to do. So VASP gives us the stress tensor, so therefore it makes sense to actually use that information. Yeah. Okay, so if they're using stress, then it's pretty much the same method. I haven't used ATA to do elastic properties calculations. We mainly focus on using it for the only place we really use ATA is for cluster expansion to do, if we're doing, if we want to do, cluster expansion to do more statistical thermodynamics type problems. Okay. Okay. So somebody was asking about getting the whole tensor as a function of different temperatures. This is not something we've implemented yet. What we can do right now is we can get the tensor as a function of pressure. So in principle, it's something we can get it as a function of pressure pretty easily, because you can get the pressure volume curve pretty easily from AGL, and then you work backwards to get so you work out what that volume would correspond to at a particular pressure, and then you can just calculate the elastic constants at that pressure. And this is something we can actually do with AFLOW. It's something that's already implemented. Doing it the same thing for temperature is not something we've implemented, because as well as just we can get so if you want to do a temperature, if you want to do the elastic constants at a particular volume, this is something we can do. There's a way to rescale the volume. I'm not going to try and get into it here, because it's something it's still in testing, basically. In principle, we could do the same thing for temperature. It's something we haven't implemented yet, but it's something that we'll consider in the future. It's going to take a little bit of time we need to test it properly, make sure everything is conceptually correct, etc. But we can also get more but we do at the moment have the bulk modulus as a function of temperature, and I'll show you how to do that with AGL now. So now I'm going to move on to the next part. Okay, so let me just make this full screen. Okay. So again, concept is pretty similar. You have this calc line that you uncomment. Then you can control the number of structures, so the number of different size cells that you have, and you can also control the step, so what increment you use to do the compression and expansion. Then you also have a few different options for this Poisson ratio that I told you about inside this equation for the Debye temperature. So you can either set it by hand to a specific value, or you can use AEL to calculate this. So you can call AEL from within AGL to run this calculation. So if you set this parameter to on, which is usually it's the default that we're setting in that we use, that's being set by AFLOW when it generates the AFLOW.in files, is to set this to on. And you can, the same way, you run all the calculations, the Dft calculations for all the strain structures using this command. Okay, and now we have some more exercises. So again, this time we go into the AGL directory. We uncomment the appropriate lines for an AGL calculation, and we rename the lock file. So we need to do this for each one of the times we create one of these directories and want to run something. We should rename this lock file. You again use this command to create the subdirectories and then see what happens. So now make another copy of this directory. Again, rename the lock file and use the option, and then switch this AEL option to off, and then again uncomment the AGL calc line, and then see what subdirectories are created. And then finally, you go into this MGO_AEL AGL directory. Again, uncomment the appropriate line, rename the lock file, and run the command to run the post-processing. Now we can, and then find the values of the Debye temperature and the lattice thermal conductivity, again from this file AFLOW.AGL.out. Okay. So again, I'll just show you where these files are. So if we go back up to Thermomechanical, we go into AGL. Again, we see this readme_AFLOW_AGL.out. We can go inside the MGO file, do get it, AFLOW.in, And then I'll just show you what these things are. So here's the line to run AFLOW calc line. Here's the line to switch off whether it uses AEL to calculate the Poisson ratio. So you switch this on and off. Here's the number of pressures. So then you can also control this for post-processing, how many temperatures it does, how many pressures it does, the size of the pressure step. I don't see the size of the temperature step here. Here's the number of structures. Here's the strain step size, and so on. And again, we can skip some of these failed runs. Okay. So I think now we can split up into our small groups, into our different breakout rooms. And let's come back at 12:20. So do about 12 minutes for this. Hopefully that should be enough time, and then we can wrap up before lunch. Okay, it looks like people are trying to filter back in now. So I'll just start sharing my screen again, and then I'll just run through the examples quickly so we can see. Okay. So somebody's asking, is there an advantage to switching off the symmetry? So the main thing you might want to do it is if you want to check the robustness of the calculation. So you have some redundancy in the calculation. So you're basically doing the same calculation in a couple of different directions. And so then you can check that the values that are supposed to be equal to each other are still equal to each other. So you can really check how robust your calculation is. So if you have a system where you might be getting some strange results, you're not 100% convinced that this is the right elastic tensor, then you might want to switch off the symmetry and try doing the calculation again. That's probably the main one. Exactly, it's safer, but it's more expensive. So, okay, so here's for the AGL calculation. So this is with the Poisson ratio switched on. Sorry, yeah, the option to calculate the Poisson ratio with AEL switched on. And here it first just generates the AEL calculations. And then you would have to run these with DFT, and then it will go again and generate the AGL calculations. If you do the other one, this time we switch the option to calculate with the Poisson ratio to off. So let me just show you the input file. So here you can see this is switched off. And here you can see it generates the AGL directories because now it doesn't need the AEL ones. Then finally, let's look at the output. Okay, so here you can see us run the post-processing for both AEL and AGL. And so now we'll open up the AGL file to see, so this aflow.agl.out file, and we'll have a look inside to see what results we get. So somebody's asking about elastic constants for disordered structures. So this is actually something we have done with POC. So, and we've actually done it for a couple of different, so if you look in, so there's actually a couple of papers we did recently where we actually used this. However, we only implemented it within the main branch of AFLOW within the last couple of weeks. So it's not really something we're advertising for others to use yet because it's a little bit tricky. And it's also can be quite computationally expensive, and it's something there still might be a few kinks we need to iron out, but otherwise, in principle, yes, this exists. We have to write some documentation. We have to write this sort of stuff. So it's not everything is 100% there yet, but in principle, the workflow does exist to combine these two different modules. And this is actually something we've been working on over the last few weeks. So let me open up the output file. So here you can see some information like the thermal conductivity. Again, we have the units, so the Debye temperature in Kelvin. We have the heat capacity at constant volume and at constant pressure at 300 Kelvin, thermal expansion, etc. And again, these are keyword value pairs. Here, we also take a note of the Poisson ratio source. So here we say that it's from AEL and we give the value that was used. Then we can also get these properties as a function of temperature. So for example, here we have the bulk modulus as a function of temperature. Here we also then do energetic properties. So we have the Gibbs free energy as a function of temperature, vibrational energy as a function of temperature, internal energy, and the vibrational entropy, all as a function of temperature again. And if you want the, so again, within the input file, there's another option. So if you want things like basically all the Gibbs free energy as a function of temperature and pressure, because this is quite a lot of data, you probably will need to do this write full results to on. Okay. Okay, so it's just coming up to 12:30 Central Time now. So unless anybody has any other questions about this. So are these outputs able to be ingested with some Python module? So I don't think there's a specific Python module we've written yet to handle these inputs. This is actually something we're still working on, especially for viewing. But so for example, we do have these output files. So we have this JSON file. And this reason we started to print this out is to make it Python readable. But this is something with the specific Python wrappers to implement these things. So we want to do things like, for example, to pull Gibbs free energies from multiple calculations to do things like phase diagrams. So this is something we're still working on. This also is useful for having these in JSON format. It's also useful for training things like machine learning models. Okay. And then unless anybody has any other questions, I think we can now break for lunch. And then we can meet back at 2 p.m. Central Time and then that will be, Marco will be talking about phonon properties. So it's again, something quite similar to what we're doing here, but it's a bit more accurate, but also can be a bit more computationally expensive. So it's like a higher level of computational, in terms of computational demand and computational exactness. Okay. So I'll just stop sharing my screen and we can break for lunch.